Rock here with Simpson Math. We've been talking about the unit circle definition of the trig functions. I want to expand the definition out so we can use any circle, not just the unit circle. This is the actual more classical, modern definition of the trig functions. So if I have a circle of any radius, it doesn't have to be radius 1. So the equation of that circle would be x squared plus y squared equals r squared. And such a circle would be centered at the origin in the Cartesian plane. And I draw an angle in standard position, and I use theta to represent the angle in standard position. And then that angle's terminal side will intersect the circle at a point that we will call xy. So this point here would be r0 because you're going out the radius to get to that point and you go up none at all. This point up here would be 0r because you go left and right 0 and then you go up the radius. Okay. Now, and xy is the point of intersection between the circle, whose radius is r, and the standard position angle intersecting it. Then, if you have all that in place, then cosine maps the angle to the x coordinate divided by the radius. Sine maps the angle to the y coordinate divided by the radius. Tangent maps the radian or degree measure of the angle to the y coordinate divided by the x. And then secant is the reciprocal cosine, cosecant is the reciprocal sine, and cotangent is reciprocal tangent, meaning it instead of y over x, it maps it to x over y. So that's the definition of the trig functions for when you have something other than a unit circle. Now you can imagine that if our radius was 1, suddenly you have 1s everywhere the r's are, and then you have our unit circle definition. Now, what we want to do is be able to use this definition to prove basic identities. And here's two identities that we call the quotient identities. The tangent of theta is the same thing as sine of theta divided by cos of theta. And cotangent of theta is the same thing as cosine of theta divided by sine of theta. And you want to be able to prove basic identities like this using the definition. So we're going to do that now. So we want to prove that tan of theta is equal to sine of theta over cos of theta. So we're going to choose the right-hand side. I'm going to use RHS. RHS is just saying right-hand side, and I'm going to say the right-hand side is what I have there. And so I'm just starting out with something that is given. So over here, I'm going to put my justifications for each step. You need to have justifications for each step. Okay, so let's make sure we blow that up so we can see it good enough. There we go. Then I'm just going to assume I have the right-hand side here, and I'm going to keep going until I get the left-hand side. And when I have the right is equal to the left, that's what I'm trying to prove. I'm done. So here we go. I'm going to plug in the definition for sine. The definition of sine is y over r. And I'm going to plug in the definition for cos, which is x over r. And this is just by definition. That's the definition of sine, that it maps theta to the y coordinate over the radius, and cosine maps the angle to the x coordinate over the radius, where x and y are the point of intersection between the angle and the circle, who has a radius of r. So this is by definition. Now, what I'm going to do next is multiply this fraction by 1. I'm going to use r over r. That's a 1. But I use that because I see these will reduce. So I get, or maybe I shouldn't, let's not do it that way. Let's go ahead and do the multiplication. So we get yr, because r times y over r is y over r over r. You don't multiply the top, and some students multiply the top and the bottom. That's not what I'm doing. I'm multiplying this fraction by r, but I'm also multiplying the bottom fraction by r. So I am multiplying the numerator and the denominator, but this is my numerator, and it's being multiplied by r, so I get this. And this is my denominator being multiplied by r, so I get this. And we just multiplied by r over r, which equals 1. And if you multiply by 1, we need to move that up so you can see it. If you multiply by 1, you don't change the expression's value. But we clearly see now this reduces, which is, I almost did that earlier, but we'll do it now. And that leaves me y over x when I reduce those common factors. But y over x is by definition tangent of theta. That's the definition of tangent, that it maps the angle to y over x. And so I have reached what was on the left. Remember, the left was tangent of theta. So I now have, remember on this side it's been understood to be the right hand side. So I have the right equals the left, I'm done. I put my proof complete symbol. Hopefully you have one more creative than that, and you stick to it, so I get to recognize what your proof complete symbol is. But I put it there, and I'm done with the proof. One thing to notice is that I have a nice vertical line of equal marks in my proof. So it's very easy to follow step by step. I have a justification for each step of the proof. So math made simple, Simpson math.